So we're very happy to welcome Güzin today to talk to us about bounds of for multistage mixed integer distributionally robust optimization. So she's a professor and associate chair for research in the Department of Integrated System Engineering at Ohio State. But she has received many prizes, published a bit all over. She gave plenaries and talks at ISMP, an international conference of stochastic programming, Inform's annual meeting, etc. And she also served as chair for the Stochastic Programming Society for a period of 4 years. And before that, she was also the vice chair for optimization under uncertainty for Informs. So please, Güzin, go ahead.
Thank you, Sylvia, and thank you so much for the invitation. I'm really very excited about to be part of the discrete optimization talks. As Sylvia mentioned, I'm going to be talking about bounds for multi-stage mixed integer distributionally robust optimization problems. This is joint work with Professor Francesca Maggioni, her former student who graduated, Danielle Faccini, and my former student who also graduated, Arthur Young. We had a lot of fun working across the pond here on this project. So let me start by some introduction. As we all know, actually, many real-world decision-making problems have time-evolving uncertainty, where we have to make decisions in a sequential manner, right? As part of this evolving uncertainty. Finance is one big example of this. I worked on water resources allocation, but these are everywhere, from logistics to transportation to many problems in energy. So much so that these class of problems, there are communities, different communities working on them, like stochastic optimal control, Markov decision processes. I'm more from stochastic programming side, so that's where our motivation comes from. But any of these types of modeling techniques, right, they all have some issues. For example, one of them is that, especially as we look further into the future, right, we don't know the true distributions. So one way to deal with that is to use a distributionally robust version of these problems. Another bad thing about these models is, of course, as we look further into the future, there is the curse of dimensionality. They grow exponentially in the number of stages. Yet we have actually, the community has done a lot of good work by exploiting certain structures like linearity, stagewise independence, and in the presence of binary variables, say, if the state variables are binary, then you can do some nice algorithmic advances, right? But many real-world problems still lack these special structures. Even if they have the special structures, all you get in the end is an approximation. So high quality and computationally efficient approximations and bounds are very desirable for this class of problems. Not only that, they are typically the only method that's available to us, okay? So this is what motivates our work. What we are going to do is we're going to use something called scenario grouping or scenario decomposition and convolution of risk measures. So if you're aware of risk measures like conditional value at risk, this is CVAR of CVAR type of thing, okay, in a convolution sense. And we're focused on the lower bounds for minimization problems, which is typically the focus of optimization. Upper bounds can be obtained by finding a feasible policy from the lower bound and just evaluating them. The whole thing can be described as, I have a really big problem. I cannot tackle this. This is too big for me. So I'm going to use a super old, thousands-year-old technique of like, I'm going to divide it into smaller groups, right, that I can handle. I'm going to solve these smaller problems, perhaps by parallel computing, so I save even further wall clock time, right? Once I obtain some optimal values or even any lower bound on them, I'm going to judiciously combine them, right? I'm going to combine them in an intelligent way to get a lower bound on the original problem, okay? So these are obviously, the smaller problems are much more relaxed, so I get a lower. All right, so going to the problem formulation. The type of multi-stage distributionally robust optimization we consider have this nested min-max structure. So we have a minimization. Our first stage we denote as t, time equals 0. Second stage actually becomes t equals 1. It's a finite horizon problem, so we have the last stage, capital T. And so we have that stage as cost, which can be nonlinear. We can have mixed integer, binary, different types of decisions here. We don't have structural constraints on this. And we are going to do that stage cost plus the worst case expected cost to go for the future, right? And that is given through the expectation is taken with respect to some distributions that belong to an ambiguity set. And we use actually conditional ambiguity sets, given that the stochastic process came here, what happens next from that point on? Okay, as I said, we don't have too many, any structural constraints on the problem like convexity, but one important thing is this stochastic process, we assume has finitely many realizations. In this case, this means we can represent it as a scenario tree, okay? And by the way, the original problem may not have this, but in order to solve it one way or another, you're gonna sample, you're gonna discretize, and this is our starting point. All right. So as I said, we do a conditional ambiguity set of distributions. We're going to use phi-divergences and Wasserstein distance, which I'm going to introduce next. But in order to simplify the notation, let's go with two-stage. That way I can get rid of these conditional, like these type of things and have a simple ambiguity set here. All right. So I'm in a finite case. So I have two distributions. Q is going to be my nominal distribution. This is the probability of scenario omega I, Q omega I. And there's another distribution on the same set of realizations. So the ambiguity set is going to be any distribution P that is sufficiently close to the nominal distribution Q, right? And how close is, we're going to use phi-divergences and Wasserstein distance to determine that. And again, how close we want to remain here, pay attention to this parameter rho, which is called the radius of the ambiguity set, or sometimes level of robustness, because we're going to play around with this parameter, okay? We can remain close to the nominal, or we can look at a wide variety of distributions. Obviously, these two things are going to be making this a probability vector. All right. So reminder on phi divergences. So this is actually a phi divergence between two distributions P and Q is an expectation with respect to the nominal distribution of a phi function, right, evaluated at the ratio. So if, for example, they give the same positive probability to the same scenario, then the ratio is 1, so there's no divergence. The phi divergence takes value 0. Otherwise, it's a non-negative convex function. And this is the phi divergence of many well-known phi divergences. This is the this is the phi function. This is the phi divergence on this column. So as I said, there are also families of phi divergences, and I especially want to talk about one such family, which is called the Cressy-Reid power divergence. It has a parameter theta. It has that division theta 1 minus theta, so it cannot take values 0 or 1. But as it takes different values, for example, 2, it captures modified chi-squared. 1/2 will become Hellinger distance. Another interesting case is it cannot take value 1, but as I take the limit to 1, I recover the very famous Kullback-Leibler divergence. If I take the limit to 0, I get the adjoint of Kullback-Leibler, which is Berg entropy. Okay? Reminder on Wasserstein on finite support. This is nothing but a transportation problem, transporting the nominal probability Q to another probability distribution P. And to do the minimal cost transportation, I need a distance or a cost, right, between two scenarios, omega I and omega j, and that's typically given by some norm like a 2 norm between two scenarios. By the way, again, pay attention to this because we're going to move from distance between two scenarios to distance between two scenario trees, okay? All right, so let's get to the what we are going to do. We're again determining lower bounds by scenario grouping and convolution of risk measures. So I'm going to start with talking about scenario grouping first and introduce convolution next. Again, to make this easier, I'm going to focus on two-stage case. All right, so how do we do scenario grouping or decomposition, right? We can do it in a variety of different ways. One of the easy one is the disjoint partition. So this is my original problem. Let's say I have 4 scenarios, equal probability. This is too big for me to solve, so I'm going to divide and conquer. So I'm going to chop it up into 2 disjoint groups. I take the first 2, do group 1. Within each group, I have to adjust the probabilities. And then each probability also will have equal the group probability themselves. So if I multiply them, I recover the full problem, right? By the way, here I just picked the first two, put in group 1, pick the next two, put in group 2, but I can do other things. I could have done 1 and 3, put in group 1, 3 and 2 and 4 in another group. So there's also some variation here. Hopefully we'll come to that. But one way or another, I do disjoint partitions. Another thing that comes very handy when we do distributionally robust optimization, I can actually fix a scenario. So now I have 5 scenarios, equal probability. Remember, distributionally robust is trying to be robust, right, with respect to worst case things. So if you know something that's going to cause you trouble, demand is high, your supply is low, you know automatically this is going to be a high cost scenario. So you can actually repeat the same scenario everywhere to get actually better bounds. This is a neat trick without like increasing the competition, right? You have to be careful with the probabilities, but that's easy to do. So you have to adjust the probabilities accordingly. And each group, again, in this case, have equal group probabilities themselves. So the notation, if you see like omega F, F for fixed scenarios, that's a set of fixed scenarios. In this case, it's this red one that I fixed. Okay. So what do I do next? So this is my original problem, right? I have 4 scenarios and I'm in a DRO, distributionally robust setting. So I have an ambiguity radius of the original problem rho. Now, I'm going to divide and conquer. Division, I have group 1, group 2, let's say disjoint groups. So instead of solving the original min-max problem, right? This is minimization with respect to x, maximization with respect to some set of distributions with the radius rho, original radius. Now I'm going to solve the same problem, but a much smaller one. I mean, in this case, 4 to 2, right? Half of the size. I need to use, so this was 1/4 probability here now, but in group 1, they are 1/2 probability each. So I form my ambiguity set accordingly here, okay? I solve the same min-max, but I have the freedom actually to change my radius from the original to something else, okay? So for the subgroup, we usually denote it with rho bar, okay? And I can choose rho bar 1, rho bar 2 for group 2. I solve the same min-max problem, much smaller ones. Once I solve them, I get their optimal values, okay? So now here's what I'm going to do. This is the convolution step. I have an optimal value of group 1 and an optimal value of group 2. Each group in my example has equal probability, right? So this is nothing but a discrete random variable. This discrete random variable takes 2 values, z1 star, z2 star, with nominal distribution that is 1/2, 1/2 probabilities. So I'm going to do a robustification step, right? Which is the convolution step. This, by the way, will give me some coherent risk measure, right? I'm not doing a min-max, by the way. There's no minimization with respect to x. This convolution step is super computationally cheap. All I'm doing is I'm robustifying it from some set of distributions that not only give equal probability, but can actually give, let's say this is a higher cost, it can give higher probability to z1 star, okay? Within some radius, rho double bar. So rho double bar is the upper level convolution step radius. Okay, I hope so far so good, because this is the main idea of this. All right, what I want in the end is this, at the end, the lower bar to be, I mean, essentially a lower bound on the original optimal value that I cannot compute. So a simpler case of this, I don't solve DRO, or like you can think of the radius to be 0. So I only have nominal distribution. Everything is expected value. In that case, this is basically these individual group problems are solving relaxed problems. If you're familiar with stochastic optimization programming literature, there are non-anticipativity constraints that basically say no matter what happens in the future, my decision now cannot like specify my decision for the, if I know I'm going to win the lottery, I'm going to buy the ticket. If I know I'm not going to buy the ticket, right? I cannot do that. I only have a probabilistic information and I make that decision with respect to all the probabilities, things that I know of. These ones are relaxed problems. So automatically they give me a lower bound. I take expectation, automatically I get a lower. But when I have the DRO, right, I have a lot of things going on. I have the original radius. I have each group. I have the freedom to choose my own radii to solve the group problems. And then I have the freedom to choose the radius for the convolution step, right? I have to be more careful. So next, I'm going to present sufficient conditions that guarantee me a lower bound on the original problem, because I can overshoot, I can robustify too much and go above, right? I don't want to do that. So for Crécy-Reed power divergences, for example, when theta is between 0 and 1, like Hellinger distance, or for example, Kullback-Leibler divergence or Berg entropy, I have these simple conditions. So I have to balance how much I give to the convolution step as well as to the subgroup problems so that I don't overshoot with respect to the original radius. When theta is less than 0 or greater than 1, I have a little bit more complicated condition here. And also please pay attention here that the fixed set of scenarios is, in this case, I cannot have that. For these, I can have fixed scenarios. This one I can't, okay? For variation distance J divergence and the family of chi divergence of order A with this parameter A greater than 1, we have these conditions. And again, only in this case, our results, basically sufficient conditions, cannot have fixed scenarios, but I can have fixed scenarios here. All right. What do I do for Wasserstein? This is a little bit more challenging. So I know how to solve the group problems because they are like regular Wasserstein DRO problems, which we, there are gazillion papers written in it, and we're in the finite case, so it's actually even way simpler, right? So the convolution step is a little bit more complicated because I know a distance between two scenarios, but I don't have a distance between two scenario groups, basically two scenario trees in the two stage, right? What's the distance between this one and that one? So turns out we can do this pretty easily. So the way to do it is look at the individual scenarios in group 1, look at their distances with respect to the individual scenarios in group 2, for example, this and that, this and this, these two, and then finally these two, and take the maximum of them. That will give us a distance between the two scenario trees in two stage. And if you use that to do the convolution step and satisfy this radii selection criteria, then we are good. We get a lower bound. Okay. So far I focused on two-stage. What do we do on multi-stage? So here, multi-stage, we have two different ways of coming up with lower bounds using the results that I showed you. The first one, what we refer to as first level lower bound. So this basically mimics the two-stage case that I just showed you, okay? And how does it mimic the two-stage? Because it only does the convolution at the first stage. So there's only it kind of looks at first stage, thinks about the rest of it like a giant second stage problem. So the nice thing about it is when it's applied to φ-divergences, you can still dissect the scenario tree in any way you want. No restrictions on here. You can apply this to Wasserstein only if the scenario tree is dissected at the first stage. So the multi-level lower bound is more applicable to both of them. However, it has a restriction on the way the tree must be dissected, right? So some properties of it. And this, the way it is dissected will give us a convolution that we do not once, but multiple times going backward in time, okay? In a nested manner to get a lower bound, valid lower. So let me start with the first level lower bound, right? So this one is after I dissect the scenario tree in any way I want, and I'm only going to change, I have only the freedom to change the radius of the first stage, coming off from the root node, looking at the second time period, right? So I have the freedom to change that. From 2 to the end of the planning horizon, I keep the same, the radii, the same as the original, okay? So only change this one. And then I solve my scenario subproblems and combine them by one convolution step, right? And then this rho bar 1 and the convolution step radius must satisfy the above criteria that I already gave you. If you do that, then we have a theorem which is written informally here that this will provide a valid lower bound to the full multi-stage problem, okay? Picture is worth 1,000 words. So this is my original problem that I cannot solve and get the optimal value. So I divide and conquer. I split up into 4 scenario groups by first 2, next 2, and so on and so forth. I solve these guys. Again, I can use parallel computing. So I only have the freedom to change the radius here. but I keep the second one, and if it were longer, like I keep the rest of it the same. So once I solve these, so what do? I get these guys, use the scenario, each scenario subgroup's probability as the nominal distribution, form an ambiguity set, solve only the inner max problem, right? Rho using this radius. So for example, if I'm using total variation distance, if this is satisfied with respect to the rho 1 bar and the rho double bar, then I get a lower bound. Done. So as I said, this is applicable to φ-divergences or Wasserstein distance with tree dissected only at the root node, but this is not dissected at the root node because I also split up these scenarios, right? So this will apply to any φ-divergence. Okay, so what do I do in the multi-level, and why did we even come to the multi-level? Was because even though we figured out a way to come up with a distance between two scenario trees in the two-stage case, we couldn't do this for multi-stage case. We tried different things and we found counterexamples that didn't give us a lower bound. So what we did is we mimicked the two-stage case multiple times, okay? So that's why we do the multi-level lower bound, and it actually turned out to be in some cases better than the first level. So for me to introduce this, let me first define this. Tau is going to be the last stage the scenario tree is dissected. Okay, so what does that mean? If this is my original tree, in our notation, t equals 0 is the root node, right? Here and now. And then actually the second stage is t equals 1 and then t equals 2 here. So this scenario tree is dissected at tau equals stage 1 because if you look at these nodes, right? The rest of the tree here, the children of that node are exactly the same as the original tree. Same for this node, which is this one. Okay, so it's dissected at 2. However, if I also like split up these 1, 2, 3, 4, 5, 6, etc., then I dissect up to tau equals 2, okay? So now this will give me a specific way to dissect a scenario tree. I'm not going to get into detail of how to do this, but the biggest implication of this is this way of dissecting the tree. If I dissect the tree up to stage tau, then this will form a refinement of the tree dissected up to stage tau minus 1. What does this mean? Again, let me use the pictures. So I got my original tree. I dissect up to tau equals 1. Now, think of this as my original scenario tree. And I dissected, again, I took the 1, 2, put it here, 3, 4 here. So this is nothing but a refinement of this tree. These two are the same refinement of that. And then these two will be the refinement of the original tree. So I actually get a nested way of splitting up the tree. So if I do that, then here is how the multi-level works. For stage 1, up to tau, the last stage that I dissect the tree, I have the freedom to choose my radii to solve the subgroup problems, okay? And each subgroup from tau plus 1 to the end of the planning horizon, I must keep the same radii as the original problem. By the way we dissect the scenario tree, starting from tau plus 1, the rest of the tree will actually follow exactly the children, grandchildren, whatever, are going to be exactly as the original tree, okay? So we keep the radii the same. Then we're going to start convoluting at stage tau. The part that forms a refinement of an upper level, we're going to convolute them, right? We're going to convolute. So now we go to tau minus 1. We're going to convolute again, go up to basically from tau to 1. And then we have the freedom to pick the radius for the convolution step. Now, at each stage, from tau up to stage 1, we satisfy the criteria I gave you earlier, then we are guaranteed to get a valid lower bound with this method, okay? Again, pictures. This is my original problem. I actually split up in exactly the same way. Now I'm using the Wasserstein distance, right? So I have to satisfy this criteria. I solve the sub-problems, I get their optimal values. Now, remember, the first two is going to be sort of will give me something about this. The other two will give me something about the other part of the tree. So let's go back here. So I solve these. Now I have freedom to choose not only row bar 1, but I can also change row bar 2. Okay, in the first level, I was only able to change this one. Now I can change both, okay, because it's dissected up to stage tau equals 2. Now, once I solve these two guys, right, I'm going to convolute these two to get a lower bound, basically, on this. I don't solve this, but I get a lower bound on this by this convolution step. Same thing here. I take these two, convolute with this radius, and I get a lower bound on this optimal value. Now I have these two. Now I'm going to convolute again, okay? One thing I want to say is when using the Wasserstein distance, when I'm doing the convolution step here, now, by the way the scenario tree is dissected, these guys are equal to one another. So I can use 1, 3, 1, 4, 2, 3, 3, 4 as my scenario sort of distance. Same thing here, right? Take the maximum of those and I do the convolution step. When I come here, I treat this as a two-stage problem. This is a giant second stage. You can think of giant second stage. I don't care what happens. So to do the convolution step, I basically look at the distance between these two nodes, which is the distance between those two nodes to do this convolution. This way, I can actually, by mimicking the two-stage distance at every time point, I can convolute and guarantee get a lower bound on this. All right. I have no time to present computational results, okay? I'm aware of this. What I'm going to do is I'm going to just talk about the takeaways in a couple of minutes. So the first one is very easy. If I have a larger subgroup problem, right? This is more representative of the original problem, so I'm going to get a better lower bound. But of course, this is going to come at a computational expense, right? I need to solve bigger subgroup problems. Another thing is fixing certain high-cost scenarios. As I said, because we are solving distributionally robust, we are trying to robustify. If you can easily identify these high-cost scenarios and repeat them, we have observed, for example, variation distance or Wasserstein distance, with no additional computational burden, you increase the lower bounds significantly, okay? And it turns out when the size of subgroups, so basically if you dissect too many times, the multi-level lower bound is going to be a lot more effective than the first level lower bound. Why? So here's a comparison of the two things that I talked to you about in this specific case. Same example, same subgroups. What happens when you do the convolution step, right? You have more freedom to robustify and get a lower bound. This is when you have basically sub-problems. If you dissect up to stage 5, 6, etc., multi-level typically gives you a better lower bound, okay? Because your scenario sub-problems are very like sparse. They have very few number of scenarios. And this way you robustify. So if you dissect up to a really high level, you know, tau 5, 6, 7, 8, something, then you get a much better bound using this. Okay. So another thing is, I told you, you can basically, you know, even if you do disjoint groups, you can form like, why did I take first two, next two? So you can basically, if you diversify these guys, you're going to get a better lower bound. And how do I pick what radius I use for my subgroups versus what radius I use for convolution? This is what happens. So just a general kind of a rule. So if this is my original tree with 16 scenarios, one extreme cases, I basically turn it into 16 deterministic single scenario problems, right? So each subgroup, I have sort of row bar max, or let's say they're all equal. But take a look, if it's one scenario, it's a deterministic problem. What is the ambiguity set? There's no ambiguity set. No matter what I pick, it has to be probability 1. So why do I waste my budget, robustness budget there? I set them all equal to 0. So I solve expected value problem, which is equivalent to the deterministic problem, right? Done. Now I have 16 things to combine in the convolution step. So I have a lot of more wiggle room. So I should actually use all my budget at the top level. So I basically set the row double bar equal to my budget, okay? Now here is the other. I have one big problem, but I cannot solve it. So the other thing is, instead of one, I have 2 subgroups, right? If I do 2 subgroups, I have 8 scenarios here. So this one, it's not like exactly equal to this, but basically you have 8 things in each subgroup, so you have a lot more wiggle room. So you should use most of your budget, robustness budget, basically solve DROs here closer to the original DRO radius. But when you combine, you're only combining two things. You don't have that much wiggle room. So that one, you should do either expectation or close to expectation, okay? But when you have 4, 4, then it depends. So you give half and half, something like that. Okay, so I'm gonna end the talk here. I thank you for your attention. This is already published in SIME Journal on Optimization. If you're interested, here's the link to the paper. I'm happy to take any talks, I guess, in the breakout rooms. Thank you so much.
Thank you very much. I will stop the recording now.